make sure that I remember to press record. Okay. Well, today we are super thankful to have Clément de Chaisemartin. Today, he is a professor in the Econ department at Sciences Po, affiliated with ENBER and JPAL. And today he's going to be presenting joint work with, I'm sorry if I get this wrong, Javier Dapol, which is going to be two-way fixed effects regressions with several treatments. And then following this, we'll have a presentation by Jimena Rico-Straffon, who is going to be presenting how implementation with one of her papers and application. So without further ado, thank you, Clément, and I'll pass it over to you. Questions welcome throughout, and I will be reading the chat.
Okay, thanks very much, Taylor, for the invitation and the introduction. So I'm excited to be presenting this work. And if that's okay, I'm actually going to start by a broader introduction about this literature, because that's going to help us understand what we are specifically doing in this paper. So in a previous paper, our AR paper, we had actually conducted a survey of all the empirical papers published by the AR from 2010 to 12. And we had found that 20% of them use a two-way fixed effects regression to measure the effect of a treatment on an outcome. So typically you would be regressing employment in county GERT on county fixed effects, ER fixed effects, and the minimum wage in county G and ERT. So we actually have a more up-to-date survey where we used a slightly different surveying method. We looked at the 100 most cited 2015 to 2019 AR papers. And the results are even more staggering because there it's 26, so 26% of them, even without restricting attention to empirical papers, use a two-way fixed effects regression. So those are really all over the place. They really are like the workhorse econometric method that people use in applied economics. So it's been well known for a long time that if a common trends assumption holds, and if the treatment effect of every unit is equal to some constant delta, then the two-way fixed effects coefficient beta identifies delta. Now, in practice, it's often obviously implausible that the treatment effect is constant. For instance, the effect of the minimum wage may differ in California and in Michigan, or it could change over time. And so the question we had asked in this AR paper is, what do those regressions identify if the effect is heterogeneous between units or over time? And we had shown that if you only assume parallel trends, but you do not assume constant treatment effect, then beta identifies the expectation of a weighted sum of the treatment effects in every group and in every time period. So you may be estimating something like 4 times the minimum wage effect in California 1993, minus 3 times the minimum wage effect in New Jersey 1992. So the WGT weights are not equal to the proportion that units in cell GT account for in the full population. And because of that, beta differs from the average treatment effect. But perhaps more worryingly, many of the WGT weights are actually strictly negative. And because of that, beta could, for instance, be strictly negative, even if the treatment effect is strictly positive in every group and at every time period. For instance, 2 times 1 minus 1 times 3, which is a weighted sum of the strictly positive numbers 1 and 3, is strictly negative. The weights attached to any two-way fixed effects regression can be computed, and we recommend computing those weights to diagnose beta's robustness to heterogeneous treatment effects. And we actually have state on R commands that compute the weights for you that are called two-way FE weights. And in practice, it turns out that in simple designs, like staggered designs with a binary treatment, so staggered means that the treatment can only switch in but cannot switch out. So in this type of simple design, the weights are often all positive. And so you may not be estimating the average treatment effect, but at least you're estimating a convex combination of treatment effects. Having only positive weights is unfortunately much less likely in more complicated designs where the treatment could be binary but switch on and off, or the treatment could just be not binary. But in any case, I think it's worth checking the weights attached to your two-way fixed effects regression. So now, where do those negative weights come from? So they come from the fact that beta in two-way fixed effects regression makes two types of forbidden comparisons, to borrow the terminology from Borusiak and co-authors. So in the case where the treatment is binary and the design is staggered, beta is a weighted average of two types of diffs in diffs. Clean diffs in diff, the one in green, that compare the outcome evolution between groups becoming treated in T and groups untreated at both dates, the never treated. And non-clean diffs in diff, the ones in red, that compare the outcome evolution of those switching groups, the switchers that become treated at T, to groups that are treated at both dates. In period T-1, the switchers are untreated, and therefore their outcome is their untreated potential outcome. At period T, they are treated, so their outcome is their outcome with the treatment, which we can rewrite as the sum of their untreated outcome plus their treatment effect. When we take the difference between these two outcomes, we get the evolution of the outcome without the treatment, plus the treatment effect of the switchers at time t. Now let's do the same math for the always treated that also enter into DID2. Those always treated are treated at T-1. So for them, even at T-1, their outcome is actually their untreated outcome plus their treatment effect. And accordingly, when you first difference their outcome, you get the first difference of their untreated potential outcome, but also the change of their treatment effect from T-1 to 2. Then DID2 is the difference between this quantity here and that one here. Under a parallel trends assumption, those evolution of the untreated potential outcome are the same, so they cancel out. And you are left with this equality here, a weighted sum of 3 treatment effects with weights summing to 1, but with 1 negative weight. And so you see that the treatment effect of the always treated at period t is going to enter with a negative sign in DID of 2, and accordingly, it's also going to enter with a negative weight in beta. And so here you see that if you were to assume that the treatment effect does not change over time, those two effects would be the same and would cancel out, and the problem would disappear. So the problem only arises if the treatment effect is heterogeneous over time. And so all the points I'm making here have been made one way or another in these 3 papers that I'm listing here. Now, when the treatment is not binary or the design is not staggered, beta is going to make a second type of forbidden comparison. Essentially, it's going to compare the outcome evolution in groups whose treatment increases more and in groups whose treatment increases less. I'm going to denote those SM and SL, switching more, switching less. I may have a group going from 0 to 4 units of treatment, and I'm going to compare it to a group going from 0 to 2 units of treatment. So those third type of DID, DID3, compare the outcome evolution of the switching more and the switching less. To simplify, let's assume that the potential outcomes follow a linear treatment effect model where the treatment effect in the switching more groups is captured by this slope delta SM and by this slope delta SL for the switching less groups. And I'm going to assume that the treatment effect is larger for the switching less groups, actually 3 times larger than in the switching more groups, but both groups have a strictly positive treatment effect. Now I'm going to assume that the switching more group go from 0 to 2 units of treatment, while the switching less go from 0 to 1 units of treatment. And then the outcome evolution of the switching more group, well, in period t-1, they're untreated, so that's just their potential outcome without the treatment. But in period t, they receive 2 units of treatment, so their outcome is their outcome without treatment plus 2 times their treatment effect, which we can rewrite as follows. And then using the fact that we've assumed that the switching more have a treatment effect that's a third of that of the switching less, this term is actually 2/3 times the slope of the switching less groups. Similarly, the switching less group have, so in period 1, they receive 1 unit, on period t, sorry, they receive 1 unit of treatment, so their outcome is their untreated outcome plus their treatment effect, minus their outcome in period t-1, which is just their untreated outcome. DID3 takes the difference between this and that, and accordingly, you see that DID3 is going to be minus 1/3 of the slope of the switching less groups, which is strictly negative, while again, the treatment effect is strictly positive for everyone. And here, the problem only arises if the treatment effect is heterogeneous across groups. If those 2 slopes were to be the same, then the problem would disappear. Okay, so the former problem arose because of heterogeneity over time. Now the problem with this second type of forbidden comparisons arises because of treatment effect heterogeneity across groups. And here, the points I'm summarizing here have been made in our paper with Xavier about fuzzy differences in differences in the restudy. So in our AER paper, we had proposed an alternative estimator, the DIDM estimator, whose building blocks are diffs in diffs comparing the outcome evolution in groups going from untreated to treated from t-1 to t, and in groups untreated at both dates, but also diff in diff estimators comparing the evolution, the outcome evolution in groups going from treated to untreated, so the switchers out, compared to groups treated at both dates. So the idea of our estimator was to say, we're going to compare switchers to non-switchers, making sure that the controls we use for a switcher had the same treatment as that switcher in t-1. And that ensures that this estimator is only going to rely on parallel trends assumption rather than homogeneous treatment effect assumption. And this estimator identifies the treatment effect on the switchers at the time that they switch, and it's computed by our DID multiple GT state on our packages. Now let's take one step back. So the two-way fixed effects regression is trying to estimate the effect of the current treatment on the current outcome. Now, past treatments could also have an effect on the outcome. And to estimate those dynamic effects, when the treatment is binary and follows a staggered design, researchers have often estimated what are called dynamic two-way fixed effect regression or event study regression. You're regressing YGT on group and time fixed effects and on indicators for how long ago did group G start receiving the treatment. And the hope when people estimate those regressions is that for L greater than 0, beta L is going to estimate the cumulative effect of L+1 treatment periods. And for L lower than 0, beta L is going to be a placebo testing the parallel trends assumption. Now, unfortunately, that hope is not quite met by reality, because Sun and Abraham showed that actually beta L in that second regression identifies a weighted sum of treatment effects with negative weights, similar to our result for static two-way fixed effects regressions. And also an interesting aspect of their result is that, for instance, beta 3, the coefficient supposed to measure the effect of 4 treatment periods, incorporates the effect of having been treated for, say, 2 or 5 periods. And accordingly, these regressions are neither robust to heterogeneous or dynamic treatment effects. So in our previous paper, we had implicitly ruled out dynamic effects, which raises the question of whether this DIDM estimator is still a valid estimator if you do have dynamic effects. And if so, because that estimator was an estimator of the instantaneous treatment effect, the effect of the current treatment on the outcome, would it be possible to extend it to estimate dynamic effects? And so the answer to those questions is going to depend a lot on the design, because the answer is actually positive in staggered designs with a binary treatment. Why is that? Well, that's because in that case, DIDM compares the outcome evolution of groups going from untreated to treated to group untreated at T-1 and T. But in a staggered design, a group untreated at T-1 and T has actually been untreated since the start of the panel. So effectively, DIDM is comparing those that get treated for the first time at T to the not yet treated at T. And accordingly, it's possible to show that under a common trend assumption of the never treated outcome, now, because we allow for dynamic effects, we change the notation and have potential outcomes that can depend not only on your current, but also on your past treatments. So under a common trend assumption on this never treated outcome, it's possible to show that DIDM is going to be unbiased for switchers treatment effect at the first period where they're treated. So this estimator remains a valid estimator if you allow for dynamic effects when the treatment is binary and your design is staggered. Now, this estimator only estimates the treatment effect at the time when switchers switch, and to estimate that treatment effects in the next period, you can compare the outcome evolution of the first time treated and the not yet treated, not from T-1 to T, but say from T-1 to T+1, T-1 to T+2, etc., long differences to look at treatment effects further out. And this strategy that I'm outlining now is one of the estimation strategy that's been proposed by Callaway and Santana. And Sun and Abraham also propose estimators of instantaneous and cumulative treatment effects in staggered designs using never treated as controls. Now, going back to the question of whether the DIDM estimator is robust to dynamic effects, the answer is no if the design is not staggered or the treatment is not binary. Again, remember, DIDM uses as controls groups untreated in T-1 and T. But if your design is not staggered, a group that's been untreated at T-1 and T may very well have been treated in T-2. And that treatment switch from T-2 to T-1 could still affect their period T outcome, in which case they're going to be invalid controls to infer the counterfactual trend that groups that switched from T-1 to T would have experienced without the switch. And so in our new paper on dynamic effects, we're going to propose dynamic treatment effect estimators that are valid, even if the design is not staggered or the treatment is not binary. Those estimators generalize some of those in Callaway and Santana, And the idea is, so in a staggered design, you would compare the first time treated to the not yet treated. When the design is not staggered or the treatment is not binary, you're going to compare the first time switchers to the not yet switchers. You're going to compare groups whose treatment changes for the first time at T to groups whose treatment has not changed yet at T. And those estimators are also computed by our state-on-R DID multiple GT packages if the robust dynamic option is requested. Okay, so what are we going to do today? So today we're going to talk of the case where you have several treatment variables you're interested in and that change over the duration of the panel. For instance, you may be interested in the effect of marijuana laws on marijuana consumption, but there are two types of laws that can be passed. You can authorize medical marijuana or you can authorize recreational marijuana. And you may want to separately estimate the effects of these two treatments. For instance, you could want to know what is the incremental effect of a recreational law on consumption rather than measuring the combined effect of those two treatments. A very intuitive idea to answer that question is to run a two-way fixed effects regression with two treatments. You would be regressing consumption of marijuana in state G ERT on state fixed effects, ERT fixed effects, whether state G ERT has a medical law and whether state G ERT has a recreational law. We're going to see that this is actually not a great idea. We're going to show that beta Fe, the coefficient on the first treatment here, identifies something that's even less interpretable than in the case where there is only one treatment in the regression. And we're going to propose two alternative estimators. When in applications where it's plausible to assume that there are no dynamic effects, we're going to propose a new estimator that generalizes our DIDM estimator. And when researchers want to allow for a dynamic effect, we're going to restrict attention to the case where the treatments are binary and follow a staggered adoption design. And in that case, we're going to propose new estimators that generalize those in Callaway and Santana. Okay, so now let's get into the detail of the setup and the assumptions. We have data that can be divided into G group and T time periods. NGT is the number of observations in group G and at period T. We are interested in the effect of K treatments. To simplify, I'm going to assume that K is 2. We have two treatment variables of interest, but generalizations to K greater than 2 are straightforward. I'm also going to assume that those treatments are binary variables, but again, results can be extended to any other treatment. And the KIGT is going to denote the value of treatment K for observation I in group G at period T. Each of those observations is going to have 4 potential outcomes because those two binary treatments can now take 4 values, 0, 0, 0, 1, 1, 0, 1, 1. The observed outcome is defined here. And then for most of the analysis, we can just aggregate everything at the GT level. So DK, GT, YGT, D, etc., are averages of the treatments, potential outcomes, etc., at the group and time level. And finally, DGT is going to stack the two treatments of group G at period T. Okay, so we're going to make some assumptions, and actually, if that's okay, I thought it was only PhD students in the audience, so I designed something a little bit like I teach in my PhD students, meaning that I'm going to ask you questions. I'm not going to be the only one talking throughout. I hope that's okay. And I'm going to ask you to interpret assumptions 3 and 4. So, but let's start with 1 and 2. So we're going to assume that the design is sharp. That means that the treatment is assigned at the GT level, which is the case in the medical and recreational marijuana law example. Everyone in the same state and year faces the same laws. Then I'm going to assume that that the vectors of potential outcomes and treatments of every group are independent. So that I'm allowing for serial correlation within group. So the consumption of Colorado in year T could be correlated with marijuana consumption in year T+1. But I'm assuming that Colorado and California have independent consumptions. Whether or not it's a good assumption, I'm not going to discuss that too much. The only thing I want to say is that whenever researchers cluster their standard errors at the group level, which is what people tend to do following the Bertrand Duflo Muller paper, implicitly that's the assumption they are making. Okay, so now let's look at assumption 3. Could someone try to explain to me what this assumption means and what it's actually ruling out, in which case it would be violated? Okay, so I see someone says, yes, exactly. So Akash is saying that the law was implemented regardless of the behavior of the outcome Y. So what would lead to a violation of this assumption here in the marijuana law example would be a case where Colorado decides to pass a recreational law because prior to that, in the previous years, consumption has been, say, increasing. Okay, if the decision to pass a law is related to trends affecting the untreated potential outcome, that would lead to a violation of this assumption. And those type of phenomena are called Ashenfelter's dip. The reason why you get treated is because you've experienced a series of negative or positive shocks on your outcome. If there is an Ashenfelter's dip phenomenon in the data, that would lead to a violation of this assumption. Yeah, that's Akash is saying that it could be violated in the US because of the opioid crisis, which could be a possibility. Now, the good news is that we're going to be able to test those assumptions. So, but let me describe the second one. So the second one requires, it's a parallel trends assumption that requires that the evolution of the untreated outcome over time is the same in every group. In the absence of any law, Colorado and California would have experienced the same evolution of their marijuana consumption. Okay, so it turns out that those are strong assumptions that should not be taken for granted. But the good news is that you can test those assumptions by looking at pre-trends, by looking at treated and control groups followed parallel trends before the treated got treated. Okay, and those pre-trends tests are implemented by most of the new packages available out there to compute DID estimators robust to heterogeneous effects. And for instance, our DID multiple GT package has a placebo option that allows you to compute several placebo estimators that all look at pre-trends. Okay, so now I'm going to define by beta at Fi the coefficient of the first treatment in a two-way fixed effects regression with both D12 and D2, the D1 and D2, sorry, the two treatment variables. And beta Fi, our estimate of interest, is going to be the expectation of that coefficient. Okay, so our first result is going to be a decomposition of two-way fixed effects regressions with several treatments. I'm going to denote by epsilon GT the residual in a regression of D1 GT. So in a regression of whether cell GT has a medical law on group and period fixed effects, and D2 GT, whether that same cell has a recreational law. Okay, so epsilon GT, to obtain it, you just regress the first treatment on group and period fixed effects and the second treatment. Then WGT is epsilon GT renormalized by the average of those epsilon GTs across the treated, across the GTs that have that received the first treatment. Okay, so now I'm going to define two causal effects. Okay, delta 0, 1 and delta 1. So one of those, could someone explain to me what do those effects represent?
Sorry, Claire, I think Akash just had a question. I think that it was related to the last slide. Just asking, does DE3 exist? A combination of both laws.
Yes, so I'm not assuming anything about whether the laws are mutually exclusive or not. So you could have both, you could receive both D1 and D2. Okay, so what is delta 0, 1 measuring?
It's a weighted average of outcomes where the weight is going to be related to the size of the group, the treated group. I forget the ordering here of the treatment. It's for the switchers going from 0 to on.
Yeah, exactly. So it's moving which treatment from 0 to 1? So it's the effect of moving the second treatment from 0 to 1 while keeping the first treatment at 0. Okay, and that's the average effect of doing that in group GERT. So that would be, for instance, the average effect. So it's not a very good example, the medical and the recreational example in this one, but that would be the effect of passing a recreational law without having a medical law. Okay, average effect of that in group GERT. Now, that one here is actually the effect of moving the first treatment from 0 to 1, so the effect of passing a medical law, while keeping the second treatment at its observed value. Okay, so that one here measures the effect of the second treatment on the outcome, while this one measures the effect of the first treatment on the outcome. So then we have the following result. We have that beta FE identifies an expectation, so it's complicated to say, an expectation of the sum of two weighted sums. Okay. The first weighted sum is a weighted sum of the effects of the first treatment on the outcome. And the second weighted sum includes effects of the second treatment on the outcome. The weights entering the first summation sum to 1, and the weights entering the second summation sum to 0. So let's interpret a little bit this theorem. So this theorem is telling us that if you run two-way fixed effects with two treatments, the coefficient on the first treatment is going to identify the sum of two things. The first thing is a weighted sum of the effect of moving that first treatment of from 0 to 1, with weights that may be positive, may be negative, but that sum to 1. So that first term is very similar to what we had in our AR paper. The new term is the second term, which actually comes from the effects of moving the second treatment from 0 to 1. The weights entering that summation sum to 0. And accordingly, if this thing here, if this delta 01 GT actually does not vary across G and T, it's just a constant, you can pull it out of the summation, and then the weights sum to 0, and so that term vanishes. So with constant effects, that second term here, you can forget about it. But with heterogeneous effects, that term is not going to disappear. And so that shows that two-way fixed effects regressions with two treatments, on top of not being robust to heterogeneous effects, which was already the case with only one treatment in the regression, now the coefficient on the first treatment can also be contaminated by the effect of the second treatment on the outcome. You think that you're measuring the effect of recreational laws, controlling for medical laws, but you are actually, to some extent, not only measuring the effect of recreational laws, but also the effect of medical laws. Okay, you have this contamination phenomenon that's new. So now, just a side note, let's get back to a setup with only one treatment. Oftentimes, researchers want to use two-way fixed effects to look at heterogeneous treatment effects. And the way they do that is that they interact their treatment with a group level binary variable IG and with 1 minus IG. For instance, you want to know if the treatment effect differs in poor and rich counties. You're going to interact your treatment with an indicator for counties above the median income and an indicator for counties below the median income. Now, these regressions can be analyzed exactly in the same way as regressions with two treatments. And this theorem here also applies to those regressions. And you have that the coefficient of the treatment interacted with rich county, the rich indicator is going to identify a weighted sum of the effects in rich counties plus a weighted sum of the effects in poor counties. So you're trying to isolate the effects in rich and in poor counties. Well, too bad for you. Turns out that your coefficient for the rich counties is actually contaminated by the effect in poor counties. Okay, so how does that fit in the literature, this theorem 1 that we've just seen? So L 2018 has a paper about movers design, and there he has one equation that's not a decomposition result as I have in theorem 1, but which is, to my knowledge, the first instance where a contamination phenomenon was shown. Another related result is Abram and Soon, who study event study regressions, which are a specific example of two-way fixed effects regressions with several treatments, where the several treatments are indicators for having started receiving the treatment L periods ago. And they show that the effects of being treated for L prime periods could contaminate the coefficient measuring the effect of L treatment periods. So our result is related to that. There as well, there is a contamination phenomenon, but it applies to situations where the treatment variables are completely different policies that may not be mutually exclusive, that may not be binary and may not follow a staggered design. And finally, this result is also related to a recent paper by Goldsmith-Spinkham et al., who showed that this contamination phenomenon also arises in linear regressions with several treatments under a conditional independence assumption rather than parallel trends. Here I'm assuming parallel trends, they assume conditional independence. And so overall, all of these papers show that this contamination phenomenon in OLS regression with several treatments is very pervasive. It arises under several types of identifying assumptions and irrespective of the nature of the treatments in the regression. Yes, Kelly?
So I assume this is true, but I want to verify with you. So if it's the case that there is some other policy that you're not particularly interested in the impact of, but you're concerned that it affects your outcome of interest and the implementation of it might be correlated with the policy that you're interested in, then in an old world, we would just want to control for that policy. So, but what I assume is regardless of whether you're interested in the impact of it or not, just by virtue of putting it in there, it's causing problems. So my question is, in the multiple GT command, where there is the subcommand or the option for controls, is that just for things that are not changing over time, or can a policy that's changing over time that I just want to control for be used in that option?
No, actually, it should not be used in that option. You're right that the controls option is only for things that, at least in principle, are not directly affecting the outcome. For things that are time varying and that may affect the outcome, you need to you can still use the command, but you need to use other strategies to do so. And actually, Jimena is going to give you a demo of one of the two strategies you may then use. But yeah, thanks for a good question. So let's see how I'm doing on time. Okay, so so the first novel thing about two-way fixed effects regressions is that with several treatments is that you may have this contamination phenomenon. You also have negative weights. That's not new. That was already there in the one treatment case, but adding treatments to your two-way fixed effects regression is going to, in general, increase the negative weights. You're going to have more negative weights in two-way fixed effects regression with several treatments than in two-way fixed effects with only one treatment, and they're going to tend to be larger. And actually, we have this result that considers the simplest possible design you can think of with two treatments. We just assume a standard diffin diff with two treatments. You have some groups that start receiving a first treatment at day T1, and a subset of those groups then start receiving a second treatment at a day T2. But you have no variation in treatment timing. Everybody receives treatment 1 at T1, and everybody receives treatment 2 at T2. Okay, no variation in treatment timing. Without variation in treatment timing, it follows from our AER paper and a little bit of algebra, because that's actually not a result we had shown in there, but that's a consequence of the result that with one treatment and no variation in treatment timing, two-way fixed effects is doing what it should be doing. It's estimating a weighted average of treatment effects with positive weights. And in fact, you can even show that it's estimating the ATT, the average treatment effect on the treated. Now, with the same design, without variation in treatment timing, but with two treatments, if you run two-way fixed effects on these two treatments, what this corollary is saying here is that you may end up having some negative weights, okay? Even in a very basic design. And more generally, beyond this, very stereotypical design without variation in treatment timing, we're going to see, if we have time to go over the application, that in a real life application, negative weights tend to be much larger in two-way fixed effects regressions with several treatments rather than only one treatment. Okay, so I'm going to present now the two alternative estimators. So first, what is going to be the target parameter for the first estimator. So it's going to be we're going to target cells whose first treatment is changing between T-1 and T, while their second treatment is not changing. And that's important because that's how we're going to be able to isolate what's really coming only from the effect of the first treatment, not the effect of the second one. And then the second requirement is that we need to have at least one control for that cell. We need to have at least one other group G prime whose treatments are not changing from T-1 to T, and that had the same two treatments as group G in T-1. So for instance, Colorado 2012 would belong to this switching cells set because it passed a recreational law in 2012 without changing its medical law. So the first treatment changed, second treatment did not change. And there are other states that had the same treatments as Colorado in 2011, meaning a medical law and no recreational law, but that did not change any of their treatments in 2012. And so that means that we're going to be able to use those states as controls to infer what would have been marijuana consumption in Colorado in 2012 if it had not passed a recreational law in that year. Okay, and our target parameter is going to be the average effect of switching the first treatment from 0 to 1 while keeping the second treatment at its observed value across all of those cells which change their first treatment without changing the second one and have a proper control that we can use. Yes, Kelly, go ahead.
So what happens if the first point 2 there is violated? What happens if you try to do this estimation and let's say because one of your treatments is already multi-valued to begin with, or maybe both of them are, and maybe there's more than 2, there are lots of treatments and they're all multi-valued. And so at some point you're just not going to have that group for comparison. What actually happens in the estimation?
So you're asking about if condition 2 fails, right?
Yes.
Then so in practice, what's gonna end up happening if you run DID multiple GT, trying to compute the estimator we propose, is that those cells are going to be dropped. The command is not going to be able to estimate the treatment effect of those cells, and that's why there is kind of a curse of dimensionality, like you're saying. If you start having like 10 treatments, it's going to start being very hard finding proper controls for each switching cell. And you may end up with a very noisy estimate in that case. So then there's going to be, some kind of bias variance trade-off. I'm going to be saying, okay, maybe I would want to estimate the effect of treatment 1 controlling for those 10 other treatments. I can't do that because I end up with a very noisy estimate. Maybe it's more reasonable to try to only control for 2 of those 10 treatments, which I think are really the important ones to be controlling for. And maybe I'm going to end up with a little bit of bias by doing so, but that's reducing the variance of my estimator so much because now there are so many more cells for which I can estimate the effect that maybe it's actually beneficial to do that. Make sense?
Okay. Yeah, thanks. That's what we decided. So thank you for telling me.
Oh, okay. So you can. Yeah, so this parameter, we're going to be able to estimate it under the same strong exogeneity and parallel trends conditions that I introduced earlier, but we need to make those conditions on the 4 potential outcomes. And our estimator is going to be a weighted average across D and T of DID estimators of this type. So notation gets really messy, but we're comparing groups whose first treatment goes from 0 to 1 while their second treatment is not changing to groups whose first treatment remains at 0 and their second treatment is also not changing, and it is the same as the second treatment of the switching group. And this estimator is computed by the DID multiple GT command, and the details of implementation are explained in the help file. Okay, so what about instances where you think it's plausible that the treatment has dynamic effects? Your outcome may not only be affected by your current treatment, but also by your past treatments. In that case, we propose an estimation strategy, but so in the paper we discuss how we could extend it to more general situations. But in this talk, I'm going to make a strong assumption. I'm going to assume that the two treatments are binary and they both follow a staggered adoption design. Good luck. What's lucky is that the marijuana law example actually satisfies those conditions. So the two treatments are binary. They both are weakly increasing over time, meaning that they follow staggered adoption. And also, I'm assuming that the treatment 2 is always adopted after treatment 1, which is again the case. Recreational laws always come after medical ones. So the good news is that there's going to be some things in this setup that are very easy to estimate, for which we don't need to resort to new estimators, but there's going to be things that are more difficult to estimate. We need new estimators. So under the same no anticipation and parallel trends assumption, and assumptions very close to those in Callaway and Santana, you can use our estimators of instantaneous and dynamic effects that we propose in our new paper for dynamic effects, redefining the treatment as the sum of the two treatments. Now, the caveat with that strategy is that the estimators that we propose in this paper, when you just kind of ignore the fact that you have two treatments and just take their summation, those estimators are going to give you the combined effect of the first and the second treatment. They are not going to disentangle the effect of the two treatments. Now, the good news is that estimating separately the effect of the first treatment is completely straightforward. You can just compute our estimators or those in Callaway and Santana, restricting the sample to the GTs that have not received yet the second treatment. So in the marijuana law example, if you want to estimate the effect of medical laws, you just restrict the sample to all the state times year that do not have a recreational law. What's more complicated is to estimate the effect of the second treatment. And we're going to need a supplementary assumption. And this assumption requires that the effect of the first treatment builds up over time in the same way in every group, meaning that the difference between the effect of being treated for T and T-1 periods should be the same in every group. The incremental effect of going from T-1 to T periods of the first treatment should be the same in every group. This still allows the treatment effects to vary with the number of treatment periods, and this still allows for heterogeneous treatment effects, but that's still a strong assumption. The good news is that, again, you're gonna have placebo estimators that will allow you to test the plausibility of this assumption. Now, why is this assumption needed for identification of the effect of the second treatment? Let's go back to the marijuana law example. Think of a state passing a recreational law. Without that assumption, that state may start experience a different outcome trend than control states that only have a medical law, either because of this new recreational law or because the effect of the medical law evolves differently in that state than in other states. And you would not be able to separate what's due to the recreational law from what's due to the fact that this state experiences a different evolution over time of its effect of the medical law. And that's why we need to assume that every state have the same evolution of their effect of the medical law over time to be able to pinpoint what's really due to the recreational law.
So Clément, I just have a clarification question there on that. Yeah. So kind of what we're talking about here in that assumption is that the treatments that different states are getting need to be close enough to the same in order for this assumption to kind of be satisfied, right? Is that kind of partially what we're talking about here, that you can't have a bunch of restrictions a bunch of restrictions on like who would be eligible for receiving medical marijuana in one state and not another, because you might be concerned that that assumption may not be valid.
No, yeah, that's a very good point. If the nature of the treatment is actually very heterogeneous across units, then that would make it less plausible that those effects evolve similarly over time. Yeah, that's a good point. Okay, and so because I'm running a little bit out of time, I'm just going to say how practically you can compute this new estimator. So you can run DID multiple GT. You need to restrict the sample to the GTs that already have the first treatment, so all the GTs that already have a medical law. And then you need to specify the trans non-param option with the year of the first treatment as an input to that option. And that's going to ensure that, for instance, when you are going to estimate the effect of the treatment of the recreational law for Colorado that passed its recreational law in 2012, you're only going to use as control states that passed their medical law in the same year as Colorado. And that ensures that in terms of the dynamic of the effect of their effect of the first treatment, they are going to be at the same moment of that dynamic, and then those controls are going to be valid controls under the assumptions we outlined. Okay, so very quickly, an application. So Hotz and Xiao measure the effect of daycare regulations affecting center-based daycares on the demand for family home daycare. So maybe when center-based daycares are more regulated, they become more expensive, and then the demand for family home daycare increases. But maybe when there are more regulations, the quality improves, which would reduce the demand for family home daycare. And so they regress the revenue of family home daycares in state G and year T on state fixed effects, year fixed effects, some controls, and 4 treatments, which are center-based daycare regulations. So the minimum staff to child ratio, an indicator for whether there is no such minimum, the minimum years of schooling to be a director of a center-based daycare, and an indicator for whether there is no such minimum. And the coefficient on the minimum years of schooling treatment is negative and very significant. So we use our decomposition to try to see, under parallel trends and allowing for heterogeneous effect, what this coefficient is estimating. So the coefficient on the years of schooling treatment measures a weighted sum of the effect of that treatment, in 127 state times year cells, where 63 of the effects entering the weighted sum receive a positive weight and 64 receive a negative weight. And you see that the negative weights are extremely large. They sum to -9. And then you have 3 other terms which correspond to the contamination terms. The coefficient on the years of schooling treatment is actually contaminated, for instance, by the staff to child ratio treatment. It also measures the effect of increasing the staff to child ratio. with those positive and negative weights. Okay. And what's interesting is that when you drop the other 3 treatments from the regression, you only keep the years of schooling treatment, the coefficient changes dramatically and becomes insignificant. And if you use the result from our AER paper to decompose that coefficient, it's now estimating a weighted sum of the effect of that treatment, years of schooling treatment, with positive and negative weights. But you can see that the negative weights are much smaller than in the regression with several treatments. Okay, and we compute our DIDM estimator with several treatments. So that's the estimator that assumes that there are no dynamic treatment effects. And we find that it's pretty different from the estimator that the authors had. Now I'm going to leave the floor to Jimena. So that's the first alternative estimator that we propose. Now Jimena is going to show you what she obtains in her own research when she computes the second alternative estimator that we propose, the one that's robust to dynamic treatment effects.
Okay, hi, so let me start sharing screen. Okay, can you see some slides? Okay, thank you. I'm going to first give you a little bit of a background of my paper before I get into data. So this paper is about forest concessions and FSC timber certification in the Peruvian Amazon. And it's joint work with Alex Pfaff. Oh, oopsie, let me change, stop sharing this then. Let me see. Can you see this?
Yeah.
Okay, perfect. Okay, so this paper is joint work, as I was saying, with Alex Pfaff, Jianhua Wang, Stephanie Panlasi, Colby Lokes, and Jennifer Swenson. Alex and Jennifer are professors at Duke University, and the rest of us are Duke alumni. So, as you may know, deforestation in the tropics is driven by economic activities such as agriculture or cattle ranching. So this brings challenges to policymakers because on the one hand, they want to conserve these super valuable ecosystems, but on the other hand, they also want to make sure that the local communities are developing. So the big question behind this paper is what happens to forest laws when we allow regulated economic activities inside forests? And in particular, in this setting, we are going to focus on logging concessions, which are areas of forests where companies or groups of individuals have rights to extract timber. And they have to follow certain rules. And well, this would be the first treatment. And the second treatment is that some of these logging concessions can decide whether to get a third-party certification from FSC to certify that they are following more or sustainable forest management practices. And that can help maybe sell their products in export markets. So, so this would be the second treatment. And the answer is not super obvious. As you know, in many developing countries, rules are not well enforced or monitoring is super hard. Imagine the Amazon. So it can be the case that in logging concessions, forest loss increases because they are not following the rules, or it could also be the case that these concessioners decide to really protect their boundaries from illegal logging and deforestation decreases. And then for FSC, maybe concessions are enough to stop deforestation and FSC is not having any additional effect, or maybe, yes, these stricter standards help reduce deforestation. So the answer is still a bit of an open question, and this is an early quasi-experimental evaluation of these two policies. And to the best of our knowledge, we are the first ones to use definitive estimators that are robust to heterogeneous and dynamic treatment effects. And for the case of FSC, we are able to handle the contamination problem and isolate the effect of FSC. So now moving on to the context of the data and the design. So this is a map of part of the study area in the Peruvian Amazon. These little areas are the forest concessions. The green ones are the ones that got certified. And we have data, we can create a panel data set because we observe also forest loss annually in each of these concessions between 2000 and 2013. So we're going to use this variation over space and time to identify the treatment effect. And again, just as a reminder, we have the two treatments, the logging concessions, and then those that got certified. And another important thing about the design is that concessions were granted at different points in time between 2002 and 2006, so early in the study period, but some of them got canceled at some point. And then certification, some of these concessions got certified in the second half of the study period, but also some of these certificates got canceled. So this brings challenges. So in this presentation and in this example, I'm just going to focus on the FSC effect, the second effect. So we're going to use Clément and his co-authors definitive estimator for multiple treatments to estimate the effect of FSC certification, controlling for the concession effect, the first treatment. So how are we going to do this? Well, we're going to first restrict the sample to active concession year observations. So we're going to make sure that the first treatment is active. And then we're going to run BID multiple GT. And we're going to include concession, cohort, non-parametric trends. And this will make sure that we are comparing concessions that started in the same year. So they have been treated by the first treatment, the same number of years. And finally, we're going to compute placebo estimators to test for the parallel trends assumption. So now let's move on to data. Okay. Okay, can you see my data? Okay, perfect. So we're going to, okay, I already opened the data set. So these are the concessions are the unit of analysis. We observed them for 13 years. We have two treatments, the concession and the FSC certification. We observe 512 concessions over 13 years. And then these, as I was telling you, these are the start years of the concessions. And these are the start years of the FSC certificate. And okay, so now the first thing I'm going to do is run the typical two-way fixed effects regression. So we have the percent loss is the outcome variable, what fraction of the logging concession got deforested in that year. FSC, so we have the two treatments here. We include year fixed effect, concession fixed effect, and then we cluster at the concession level. And we get that the effect of FSC is a reduction in deforestation, and it's statistically significant, and the concession effect is it's not statistically significant. But now let's see what happens with the weights. So we're going to use Clément's command, the two-way FE weights, to check what's going on. So remember, in this case, we need first the outcome variable, then the group variable, the time variable, and the treatment. We're going to include this option of FETR for fixed effect under common trends assumption. If you're running, I don't know, a first difference regression, you can include another option. And to include, we are going to include the concession dummy here in other treatments. So the result is that for FSC, we have 115 ATTs, and all of them receive a positive weight. But for the second coefficient, which is the concession effect, we have more than half, the 2,370, ATTs that receive a negative weight. So we have contamination of the coefficient of FSC certification, right? And we can see here that the negative weight sum to minus 1.375, which is pretty big. So, and just to verify, this is the same coefficient that we found here, right? So now I'm going to show you.
Just if I can interrupt 1 minute, I think
yes.
this example is very interesting because you see that it's a staggered design, and it's indeed the case that beta FE is estimating a weighted average. There are no negative weights of the effect of the treatment you're interested in. So here, the issue is really not the negative weights. All the weights are positive. The issue is like these very large contamination weights, whereby you think you're estimating the effect of the FSC treatment, but your coefficient is heavily contaminated by the other treatment in the regression, actually. Sorry, Jimena, you can go ahead.
No, it's okay. Feel free to interrupt or make questions if anybody has any questions. So I'm going to start running the other command because it takes about 2 minutes. Here, as I told you, I'm going to eliminate the inactive concession year observations. So I'm going to keep those when the concession treatment is equal to 1. And now, okay, let me explain to you the DID multiple GT command. Again, we have the outcome, the group variable, time variable, and the treatment. We cluster again at the concession level, and then we need at least 100 repetitions to bootstrap the standard errors. Then to be able to include dynamic effects, we need this robust dynamic option. And this is, let me show you how to calculate the dynamic effect, because this can be a little bit tricky. So the last observation that we have in the panel is 2013. And the first certificate was given in 2006. And then we subtract 1 from that, and we get 6 dynamic effects. That's the maximum number of dynamic effects we can have. And then for the placebo estimators, we need to go back. So it's 2006 was the first certificate. Then the first year in the panel is 2001, and then -1. That's 4 placebo estimators maximum that you can calculate. So I put them here. Then, then we want to test for the parallel trends assumption. So we need to include these options: covariances, joint test placebo, and long difference placebo. Then I also included this average effect option because this will average the dynamic effect and also the instantaneous effect, and this can be comparable to the two-way fixed effect coefficient that we found previously. You need to set seed so that you can replicate this result. And then a key thing is including the non-parametric. Oh, we have it. Let me, before I show you the result, just talk super quickly about the non-parametric trends. For the, this is the concession year, the start of each concession. The concession year. So, and then you type e-return list so that you can see all the effects. So let's go and see what the command shows you. So yeah, we can see this is the average effect. Let me compare it quickly with the two-way. This was the effect of two-way fixed effect. So we can see that it's much larger, the diff in diff, once we are able to eliminate the contamination effect. And it's also statistically significant. Then another thing that we want to check is whether the parallel trends assumption holds. And we can see that, yes, it holds. Here's the, well, again, the average effect. And okay, now let's see the graph. This is interesting. So this,
maybe just one thing here. So the P joint placebo that Jimena was showing, it's the p-value of a joint test that all the placebos are equal to 0. Because if you look at each placebo estimator individually, so here it's okay, you have only 4 of them, but sometimes you can have like 20 of them. Mechanically, you're going to find that some of those are statistically significant, so you want to run a joint test. Okay, so
yeah, or in this case, this one, for example.
Yeah, this one, for instance, is significant, yeah.
Yeah, but it passed the test. So yeah, this is the start of, so in year 0, this is the instantaneous effect, and we can see that the effects after 1 to 6 years later, and we can see that the effects are growing over time. What else? What else do I need to show you? Yeah, I think I don't know if anybody has any question. Yeah, I think I showed everything I wanted to show you. Oh, and also one thing that, one practical thing is that you might make mistakes at first on how many dynamic effects or placebo effects to include. So you can start with only, I don't know, 2 replications to see if the command runs. And yeah, and just to check, and then once you're sure that the command runs, you can move it to 100 or more replications. And in this case, it didn't take too long to run, but when I had the data at the pixel level with thousands of pixels, it took up to, I don't know, 12 hours. So sometimes you have to be patient. Yeah.
Thank you very much, Jimena. There are a couple questions in the chat. I don't know if Clément or Emilia, if either of you want to.
Yeah, so I see Natalia's question. So we see that the contamination issue was the most important problem because there were actually no negative weights. So what two-way FE weight was saying is that you know, so it's a two-way fixed effects regression with 2 treatments. So it's estimating a sum of 2 terms. The first one is a weighted sum of the effects of the first treatment in every concession on year. And what it's saying is that the sum, so it's a weighted sum of 115 ATTs of that first treatment, and 115 receive a positive weight and 0 receive a negative weight. So you don't have any negative weights in that example. Now, the second term is a weighted sum of the effects of the second treatment in more than 4,000 concession times year cells, where more than half receive a negative weight. But what's more important here is that the weights are actually pretty large. It's not like you have positive weights summing to 0.05 and negative weights summing to minus 0.05. No, it's not like that. It's like they sum to 1.4 and minus 1.4. So they could substantially bias your coefficient. Okay, so then there was a second question about clustering. Yeah, so you have a cluster option, exactly like you said, where you can specify the level at which you want the bootstrap to be clustered. And to your last question, actually, it's more a question for Jimena, but I think Jimena, correct me if I'm wrong. But so you're asking if we could. So here we are analyzing the effect of the second treatment holding the first one constant. Could we do the opposite? Well, here we cannot, because the second treatment always takes place after the first one. So we could not do the converse analysis.
Yeah, exactly. And in this case, what we ended up doing is compare it. When we analyze the effect of the first treatment, we also consider forests outside the concessions and eliminate the FSC concessions from the analysis, and that will be more of the control group. Yeah, so you have to think about other strategies to evaluate the effects of one treatment, of the first treatment.
So Esgi is asking a very good question on which I'm going to have to punt and refer her to, we have a discussion about that in the paper. So she's asking whether you can still do something when things are messier, which is oftentimes the case. And, you know, some groups start receiving the first treatment before the second, but others, for other groups, it's the opposite. And the answer is that, yes, you can do things, but things get messier. And in particular, the estimates that you get are getting less and less interpretable as your design is getting more complicated. But, you know, if you have a specific, so you can take a look at this discussion in the paper. But if you have a specific research design in mind and want to know what you could do, feel free to be in touch. I mean, this paper got started after conversations I had with Jimena and with two other teams of researchers, one of which were separately estimating the effect of recreational and medical marijuana law. So this example is not coming out of the blue. So what I mean to say is that I'm interested in these conversations because, you know, it's nice to see to help colleagues doing their research, but also because that's a way to get new ideas of interesting papers to write. So if you have a cool research design you want to talk about, I'm happy to do that. So okay, and I see. Yeah, so you can use panel data, repeated cross section. You can even have a single cross section where a birth cohort is playing the role of time, for instance. So all of those work. And to adjust for the sampling weight, you have a weight option. You can weight observations in the comment. In both, actually, two-way if you weights, but also DID multiple GT.
Awesome. So I think I'll wrap up here, and then we could, I don't know if you want to stick around to see if there are any other questions after, but we'll kind of cut here, and anyone who has to leave can do so. But I want to thank Clément very much for seeing us off with a band, and him as well for the great real life example and not just something constructed just to highlight things, but an actual real life research example is fantastic to see. So thank you both for presenting that today, and thank everyone for showing up for these reading group sessions.
Thanks everyone for coming. It's been very nice.
Yeah, thank you.
Bye-bye.